Power System Stability course, and this is particularly for third year electrical engineering students. Now let us start the power system stability. We know that the power system is a very large complex network comprising of synchronous generator, transformer, switchgear, and all components will be operating in parallel. Now, due to some fault or other operational condition change, if one component derails from synchronism, then it will affect the other components and thereby affecting the whole network. We consider 5 generators operating in parallel, and due to a fault, if any one generator loses synchronism, certainly it will affect the other generators. Now, due to this, the whole system will undergo a drastic change. So, the faulty generator must be switched out immediately. If the faulty generator is not switched out properly, then it will affect the voltage profile of the system, and there will be a wide fluctuation in voltage, and the consumer cannot operate his equipments more satisfactorily. So, due to instability, the objective of our system is lost. Now, the greater importance must be attributed to the stability of power system. In case of stability, stability denoting a condition in which various synchronous machines of the system remain in synchronism with each other. And in case of instability, it denotes a condition involving loss of synchronism. Now, the two types of stability, the first one steady state and the second one transient state. Now, the steady state condition is the operating state of power system which is characterized by gradual or relatively slow change. Now, in case of steady state stability limit, when the load on the system is increased gradually, the maximum power that can be transmitted without losing synchronism, and this is termed as a steady state stability limit. Now, the transient state is the operating state of a power system which is characterized by sudden change in load or circuit condition. Now, the transient state stability limit. In case of transient state stability limit, when the load on the system is increased suddenly, the maximum power that can be transmitted without losing synchronism, and this is termed as a transient state stability of the system for the given condition. Now, normally the steady state stability limit is greater than the transient state stability limit. Now, the classification of steady state stability limit, and it is subdivided into two parts. One is the static stability limit and another is dynamic stability limit. Now, the static stability limit refers to a steady state stability limit that prevails without the aid of regulating device. Now, the dynamic stability limit denotes steady state stability limit prevailing in an unstable system with the help of regulating device such as speed governors, voltage regulators. Now, the topic is power angle equation of a two machine system. Now, real power is given by EG/EM by X sin del, and this equation shows that the power transmitted from generator to motor varies with the sign of the displacement of angle delta between the two rotors. Now, this equation is called power angle equation. Now, power angle curve. If the curves delta versus P is plotted, then it is called the power angle curve. First, draw this picture. The maximum power occurs when delta equal to 90 degree. That means sin del equal to 1. So P max equal to Eg Em by x, and this is the steady state stability limit. When the slope del P by del del is positive, then the system is stable. When the slope del P by del del is positive, that means minus 90 less equal to 90. It means that the increase in displacement angle result in an increase in the transmitted power, and so the system will be stable. And if del P by del del is negative, that it indicates that the system is unstable. Now the topic is methods of improving steady state stability. Steady state stability limit is denoted as a Pmax. Now Pmax can be increased by the number 1 increasing either or both Eg and Em, and number 2 the reducing x. The first methods for increasing system voltage. Now the higher excitation voltage and first response excitation system substantially increase the steady state stability limit. Rising the line voltage also increases the transmission system capability. Now the second methods for reducing the reactance between stations. In this method, the number 1, the use of double circuit line. Even if one of the line fails, it can be switched off, and hence the continuity of supply can be maintained. Now the second one, use of bundle conductor. Bundling of conductor reducing the line reactance. Number 3, series compensation of line reactance. Inductive reactance of a line can be reduced by connecting static capacitors in series with the line. And the fourth one, use of synchronous phase modifiers. Synchronous phase modifiers may be installed in intermediate substation to increase the power limit. And the fifth one, use of machines with low impedance. It improves the transmission capacity. Now the topic is conventions used in motor and generator. For a synchronous generator, the input is the mechanical or shaft torque and the output is the electromagnetic torque. Now they are assumed as positive for generators. Now for a synchronous motor, the input is the electromagnetic torque and output is the shaft torque. Now based upon the sign conventions used in synchronous generator, the values of the shaft torque and the electromagnetic torque are taken as negative for a motor action. Now, electromagnetic torque T and shaft torque Ts. If the losses are neglected, the difference between the shaft torque and the electromagnetic torque is equal to the accelerating or deaccelerating torque. If T is positive, it represents accelerating torque. If T is negative, then it represents deaccelerating torque. Now, for a generator, when T is greater than T, then T is positive and the rotor accelerates. In case of synchronous motor, only when the T greater than Ts, that means T is positive, since Ts and T are both negative according to basic sign conventions. Now the topic is swing equation. The behavior of a synchronous machine during transient period is described by the swing equation. Now the torque is given by T equal to I into alpha. So you can write I d2 theta by dt square. Now I is the moment of inertia kg meter square and alpha is the angular acceleration rad per second square. And where the theta is the angular position of the rotor in radians at the instant of time. But is the time in second. Now to measure the theta with respect to a reference axis, that is the rotating at the synchronous speed, we can write the theta equal to omega st plus delta. That is electrical radiance. And where the delta is the angular displacement of rotor in electrical degrees from the synchronously rotating reference axis. And omega s is the synchronous speed in electrical radians. So I can write the theta equal to omega st plus del. Now differentiating with respect to t, we get d theta by dt equal to omega s plus d del by dt. Now differentiating once again with respect to t, we get d2 theta by dt square is equal to d2 del by dt square. Equation 5. Now the angular acceleration of rotor. That is alpha equal to, write d2 theta by dt square. Is equal to d2 del by dt square. Electrical radiance. We know that the synchronous generator, the accelerating torque TA is equal to the difference of input shaft torque, that is the Ti, and the output electromagnetic torque, that is the Tu. Equation 7. It is equal to d2 theta by dt square is equal to I d2 del by dt square. So we can write Ta equal to Ti minus Tu, that is I d2 del by dt square. Now multiplying both sides by angular velocity omega, get omega Ta is equal to omega Ti minus omega Tu, that is equal to I omega d2 del by dt square. Equation 8. So I can write Pa is equal to Pi minus Pu is equal to Iw d2 del by dt square. Equation 9. Now Pa, Pi and Pu. Pa is the accelerating power and Pi is the mechanical power input and Pu is the electrical power output. So the angular momentum M, we can write is equal to I into omega. So you can write Pa equal to Pi minus Pu is equal to M d2 del by dt square, or Pa equal to M d2 del by dt square. This is the swing equation. Equation 10. It is a nonlinear differential equation of second order. Now let us come to figure swing curve. Unstable and this is stable. We know that the swing equation Pa equal to M d2 del by dt square. Now the solution of swing equation gives the variation of del in electrical radians with respect to time in seconds. Now the graph when plotted is called as a swing curve. It provides information regarding stability. Now if delta increases continuously with time, the system is unstable. While if delta start decreasing after reaching a maximum value, then the system will remain stable. The principle by which stability under transient condition is determined without solving the swing equation is called the equal area criterion of stability. Come to this topic. Equal area criterion method applied to a machine swinging with respect to an infinite bus. The swing equation of a synchronous machine, we know that the m d2 del by dt square is equal to pa. We can write pi minus p. Or we can write d2 del by dt square equal to pa by m. Multiplying both sides by 2 d del by dt. 2 pa by m d del by dt, or d by dt, we can write d del by dt whole square is equal to 2 pa by m d del by dt, or d del by dt 2 pa by m d del. Upon integrating, we write integrate 2 pa by m d del. We can write 2 by m root 2 by m integrate pa d del. If d del by dt equal to omega, the velocity of the displacement angle with respect to the infinite bus, so you can write equal to d del by dt equal to root 2 by m integrate pa d del. Now let us come to the figure. Constant input line equal area criterion. Now under the steady operating, now for stability criterion, we can write integration pi d del equal to integration pu d, or we can write area AFGDA is equal to area BCEDGFB Now integration pi d del, we can write AF GdA. Now the integration pu d del, we can write BCEDGFB, or we can write area ABC plus area BCDGF. Now AFGDA, we can write this is equal to area ABC plus area BCDGF is equal to area BCEDGFB. We can write area CED plus area BCDGF. Area CED plus BCDGF. This is equal to BCEDGFB, or we can write area ABC is equal to area CED, or we can write this area denoted as A1 and this is the A2, so we can write A1 equal to A2. Now the area A1 below PI line is equal to the area A2 above PI line. So this method is called equal area criterion. Now look at this figure. AB represent PI minus PU, that is the accelerating power corresponding to the initial angle del 0, and DE represent PU minus PI, that is the deaccelerating power, and when accelerating power is equal to the deaccelerating power, the machine tends to return to the original condition if there is balance between the two areas at del equal to del M. Now the system will remain in stable condition when A2 greater equal to A1. If accelerating area A1 is greater than the deaccelerating area A2, then the system will definitely become unstable. We can write PE equal to E V infinity xt dash plus xt sin del, or is equal to, we can write P max sin del. Now under steady state condition, PM is equal to PE is equal to, we can write P max sin del 0. Now sudden change in mechanical input come to this figure. Just come to this figure. Sudden increase of mechanical input from PM0 to PM1. Now the operating point is shifted from A to B. Here PA equal to, we can write PM minus P, the accelerating power. Now the speed of the rotor omega increases above the synchronous speed, and the rotor angle and d del by dt also increased. Now at point B, del equal to del 1, that means PA equal to 0, but the rotor angle continues to accelerate due to inertia of the stored energy. Now the omega continues to be greater than omega s. Now at a point beyond B, say at the point C, all the stored energy in the rotor is exhausted, and the rotor speed starts reducing and the deaccelerating at del equal to del 2, and the rotor start deaccelerating. And let's see omega equal to omega s. Since the rotor is deaccelerating, the rotor angle begins to reduce. Now look at this figure. This is the oscillation of rotor. Now this is for well-damped system. The upward arrow in this figure represents d del by dt greater than 0. That is accelerating rotor. If this persists for more than 1 second, then the system might lose stability. But before 1 second or so, if it start deaccelerating, that is the d del by dt less 0, marked by the downward arrow, then the system is stable. Now the rotor oscillates about the rotor angle del 1, the upper limit being del 2 and the lower limit del 0. So look at this previous picture. Upper limit del 2 and this is the lower limit del 0. Now for the steady state condition to be reached, the PM equal to P equal to, we know that the PM equal to PE equal to P max sin del 1. That means the accelerating area should be equal to the deaccelerating area. Now write the accelerating area. We can write A1 is equal to del 0 to del 1 PM minus PE d del. Just come to this picture. A1 integration PM minus P del 0 to del 1 and A2 del 1 to del 2. So you can write decelerating area A2 is equal to del 1 to del 2 PE minus PM d del. Now del 2, we can write del max is equal to pi minus del 1. Just look at this picture. Del 2 is equal to del max, that is a pi minus del 1. So we can write pi minus sine inverse Pm1 by P max del 1 Pm1 by P max. Now del 2 is found out such that it is the maximum rotor angle beyond which the system goes out of control. Now come to the next topic. Sudden short circuit of one of the parallel lines. Just come to this figure. At point A, the short circuit fault is simulated corresponding to del equal to del 0. At point A, del equal to del 0. Now, due to this, the electrical power transferred is immediately brought to 0. That means PE equal to 0. Now, at point B, at this point, PE equal to 0, this point, and remains so till it is cleared at del equal to del CR. Now, at point C, now the fault is cleared after time TCR and corresponding angle del CR. Now, at point D, because of clearing of the fault by opening the shorted line and the heavy line transfer power, now P is increased to the point D. Now at point D, E, the rotor travels in the deaccelerating area till the point E. At E, the kinetic energy that is stored in the rotor is exhausted. Hence the rotor travels back to del CR and del 0. For steady state to be reached these two areas, that means the accelerating area A1 and the deaccelerating area A2 should be equal. Now come to the next topic. To find the critical clearing time, that is TCR. Now from swing equation, we can write d2 del by dt square, that is equal to 1 by m Pm minus Pe, or d2 del by dt square is equal to 1 by m pm. During fault, Pe equal to 0. Now integrating above equation, we get d del by dt, that is equal to 1 by m pmt. Again integrating, we get del equal to 1 by 2m pmt square plus del 0. This is equation 1. For critical clearing angle del CR, critical clearing angle del CR, time is TCR. We can write del CR equal to 1 by 2m pm TCR plus del 0. This is equation 2.